Thank you, Dr. Chanarong. So right now we can begin our final symposium. The first one will be Professor Femke Wasserpel. She is the project coordinator. She works in the TU Delft. She will be online from the Netherlands. Uh, she will talk about the project overviews and also the outcome of this study. So, Femke, are you ready?
Thank you. Yes, can I speak? I'm assuming that this is okay. Perhaps Mr. Prakrit Nopradit, can you indicate if you can hear me? Good. Thanks. Then I assume that the room can also hear me, and then I'll start. Let me start by hold on, by sharing my desktop. By saying some words of appreciation and recognition of the passing away of your Queen Mother Silikit. I understand that these days may be days of mourning, and my thoughts are with you as a country. I'd also like to pay my respect and thanks to Captain Summert, who has organized this symposium with all considerations, and has done so in very close collaboration with my colleague Wim Simons, who I really need to thank for being involved in this project in the first place, because it's Wim Simons who had all the relationships with our Thai partners. I'd also like to thank the Thai government, in particular the Ministry of Higher Education and Department of Mineral Resources and the Department of National Resources and the Environment, for having their staff and finances available in this project, and for us to make it possible to work with people in the country, which I think is essential for this project. Last year, I was visiting Bangkok in person, and I was overwhelmed by the hospitality of the people in Thailand, and I would have loved to be there again this year, but unfortunately other commitments made this impossible. But I do hope that this project is not the end, but the beginning of more projects, and that I will have the opportunity to visit you in Thailand again. Today I will give you an overview of the objectives of our project, and I will list you the outcomes of the work that we did jointly with multiple institutions involved. And I will then leave it to the other participants of this symposium to give more details on the different parts. This is the agenda of the project, and the project started 4 years ago in 2021. We were still in the Corona time, but work started quite efficiently, as mentioned, especially with the work of Wim Simons and his colleague Mark Naye in aerospace engineering in Delft, who already had this active collaboration with your country. The objective was to monitor and study subsidence, so the downward motion of the Earth's surface as a result of groundwater extraction. And to do this, by integrating numerical models which simulate downward motion with observations thereof, but also include observations of the hydrological environment, so also groundwater and pumping information. For that, we used multiple data sets, which were also very kindly provided to us by our Thai partners. I will give you today an overview of the workflow that we used, or actually two different workflows that we used, and the outcomes so far. I regret to inform you that the PhD candidate in the project, Jenny Suntorn Ransang, is no longer with TU Delft and is therefore also unable to present today, but I'll try to present her results as well as I can. And I think she has done tremendously interesting work, which really leads to future projects. Yes.
Can you put this, your slides bigger, or I don't know if it's a problem here.
I see what's happening. Thanks. I think I'm showing the wrong. This is what I wanted to show.
Okay, perfect. Thank you.
Yeah. Apologies for that. So this is what you should have seen in the first place. Thank you. Yeah, so this is what I'll share with you today. I'll give an introduction of the contributors. I'll give the objectives of our project. I'll describe the data simulation that we applied, as well as the data sets that we integrated into our workflow, and I'll give you the outcomes so far. These are the names that let me just move something along so I can see it myself a bit better. These are the names of the people involved in our project, and I am sure there are many more people involved who were more behind the scenes. But I want to greatly acknowledge again Captain Sommert of the Royal Thai Naval Academy, who together with Wim Simons have been really nurturing the relationships between the different institutes. I'm also pleased to have the collaboration of Anupal Alpert, who will present in a minute. And we were very grateful to the Department of Mineral Resources for providing geological data and GPS data, as well as to the Department of Groundwater Resources, who provided hydrological data. Then Milan Lejaki, a colleague of Professor Andrew Hopper of University of Leeds, will present later on, and as well as Wim Simons and Mark Naye, colleagues of me in TU Delft. We also collaborated with an oceanographer in the Netherlands, Dr. M.A. Slange, who has been involved in the IPCC report and is very knowledgeable about future sea level scenarios. And together we supervised an MSc student, Tijmen de Boer. During the project, we got in touch with Dr. Philip Minderhout and his student Isabel Kuhn, who from Wageningen University in the Netherlands are also working on this topic and were willing to share their insights with us. On the hydrological side, my colleague, Professor Mark Bakker, has been guiding Jenny Suntorn Ransang. And I really want to say words of appreciation for Jenny Suntorn Ransang, who has done a tremendous work of getting some results that you'll see today. I'm here showing all the pictures of the people involved. Let me make sure that you can actually see this. And I just mentioned the names, but I really want to appreciate this large team, and it's really through joint work that we were able to achieve what we did. It will be no surprise to you that the land of Bangkok is sinking, and we can also at the same time acknowledge that the global sea level is rising because of the changes in climate. We identify several causes for this, A large part of the subsidence is due to groundwater extraction, although in the past years this has been regulated a lot more, and a lot of drinking water and other water in the Bangkok area is now obtained from surface water. But in the past, the groundwater extraction was one of the major sources of subsidence, and it's therefore a very important process to study. Also, erosion, both of the river Chao Phraya, but also coastal erosion will take a part in the changing of the coastline of Bangkok. And this is also an important process to be studied. Within our project, we did not address the erosion, but this is certainly an interesting topic for further research. We believe that with our workflows, we can make a start to better monitoring and better integrate our physical knowledge with the observations, and thereby provide better scenarios to protect the Bangkok landscape. And that's the overall aim also of this project. The geology of the Bangkok area is quite complex, with 8 different aquifers laying in the first 500 meters of the subsurface, and you can see all of them numbered here. It's the first 4 aquifers that are really the most important for providing the groundwater in the Bangkok region. And without going too much in detail, you see how the different geological phases have accumulated over this region to build up that stratigraphy that we now observe in this delta region. And more details on this can be found in this paper of 2005. For our modeling study, we highly simplified this geography, and we focused on the fact that we have the different aquifers, and I'm showing you here the 4 main aquifers for groundwater supply, interlaced by clay layers, and the clay responds differently to changes in subsurface pressure than the aquifers do. And for that reason, we had specific models to model the compaction in these clay layers. And that you will see in a moment how we address that. But it's important to realize that this complex geology that I showed you before has been highly simplified in our forward model. I'm repeating here the project's objective. The objective is to develop a data assimilation approach, and data assimilation is the combination of forward modeling, so simulation by a model of the physical processes, and to combine them with data of satellites and in situ for the evaluation of subsidence resulting from groundwater extraction in this Bangkok Delta area, which is highly affected by sea level change. And then we do this to better monitor subsidence through both the in-situ leveling, the GPS observations, and the INSAR analysis, and provide a comprehensive overview. We also do this to monitor the sea level changes, and we're very pleased to have the tide gauges available to us, as well as satellite altimetry. We interpret the measured groundwater level in the observation wells and try to tie these to groundwater pumping data that we have available, and to the evaporation and precipitation data that we use. Thereby, we can evaluate expected changes of the Thai coastline for various scenarios of subsidence and groundwater production. And ultimately, we hope this will help you in Thailand to prevent and mitigate the hazards of flooding. I think you may have seen this picture at least before last year, but and it may also feature in some of the other presentations, but I like it a lot because it summarizes all the different observations that we use, and also the interplay between the solid earth and the subsidence that's happening there, as well as the sea level rise. You see here where schematically the city of Bangkok is indicated that the country is subsiding, and at the same time the sea level is rising, which means that the coastline of the mean high-rise sea level will move around along the coast. We can measure this by tracking the tide gauges, but we can complement the tide gauge data with highly accurate satellite altimeter data. At the same time, we can monitor the surface movements, the deformation, with GPS data, which are collected through GNSS stations, as well as INSAR, which provides a relative form of subsidence. And all of these different sea level and surface deformation data will need to be referenced in order to bring them together. And that's what we do by using a reference ellipsoid. The workflow of our project originally looks like this, where you see everything in green related to the groundwater processes as well as the subsidence, and everything in blue is more related to the sea level. And eventually this came together in the master project of Tijmen de Boer, where he looked at both the groundwater scenarios and the sea level scenarios, which should allow us to give high water line projections for the future, also taking into account the AR6. So those are the IPCC sea level projections. Apologies. Today, I will mostly focus on this part where the majority of our activities took place. And there, I realized that not everyone may be equally familiar with the concept of data assimilation, so I introduced one slide to explain this. Data assimilation comes from weather forecasting, and we see in weather forecasting that meteorological models are used to give a prediction. When we then have observations of the weather, we want to find what was really going on. We know that the model is not completely perfect, but we also realize that our observations are not perfect. So we combine these two types of data to Is that a question or was that? I just heard a voice, but I'll just continue. So the model can be improved. And from this improved model, we can then do another forecast. This improvement or correction of the model happens through taking into considerations the uncertainties both of the data and the model. And for that, we use the theorem of Bayes, which states that a certain model state X, given the observations, is proportional to the probability density function of the model multiplied by the likelihood of the observations. And even if you're not following completely the mathematics of this theorem, I think it's quite intuitive to realize that the data assimilation result will be a weighting of both the model outcome and the observations. And that's what we do in order to simulate and to find the best possible solutions out of the model and the observations. The data that we use in this data assimilation are, first of all, the GNNS data, where Wim Siemens is working very closely with the Asian Institute of Technology and other institutes to monitor different stations. And Wim will talk about this later on. But this is one such station where we can actually receive the signals from all the GNNS satellites that are circling around the globe. The specific GPS stations that we're using in this project are indicated here with the colors. And as said before, Wim Simons will talk more about it. And it's very important perhaps to recognize that, the group of aerospace in Delft has one of the leading GPS softwares to process these data. And that will really allow us to get a very accurate overview of the ground motion in the area. Then these data, as I mentioned before, they're absolute, but they're combined with relative ground deformation data from the INSAR satellite, which uses SAR images, synthetic aperture radar images, and performs interferometry on them in order to derive the downward or upward or even the lateral movements of the surface. And as you can see here, this is a relatively old picture, but it very nicely depicts how the coastline of Bangkok has been subsiding, especially at the end of the last century. Anuvau Albert will give a presentation on this later, and also Milan will show the latest results that he obtained with Andrew Hooper. You can see here how the area around Bangkok has really changed over the years 2005-2010. And I presume that Milan will give an update to even more recent years. Marc Naillet will follow with a presentation of the altimeter data. And the altimetry concept is explained here, where the altimeter sends a radar to the sea surface. And by recording the response, we're able to measure the distance between the satellite and the Earth's surface. And by combining this with accurate measurements of the orbital height of the satellite, we can derive the sea level relative to a reference ellipsoid. By then using an exact model of the geoid, we know what exactly is the dynamic topography, which we can then use also to forecast currents and to have a better estimate of the physics of the ocean here in the Gulf of Thailand. And that will help us eventually also to better forecast changes in sea level. These measurements are being are relatively low resolution, but by combining them with in situ tide gauges along the coast of Thailand, we're able to much better fine-tune the coastal changes in the Gulf of Thailand. But Marc Naillet is really the expert here and can tell you more about this. I'm now focusing more on the work that was done by Jenny Soontorn Rangsan at the Faculty of Civil Engineering and Geosciences in Delft in collaboration with Mark Bakker and myself. And she started to use groundwater heads from observation wells in the Bangkok area, also kindly provided to us by the Department of Groundwater Resources. And she combined it with rainfall, evaporation and temperature data that she was able to obtain for Thailand as well. She also had observations of the surface water level of the Chao Phraya River, but this was a discontinuous data set. And she used a global reanalysis of evaporation and rainfall in order to understand what natural influences occurred on the analysis. The blue arrows in this plot are the groundwater wells that she focused on in her work. And just for reference, I also indicated the GPS stations that have been used in this work. The data have then been combined to estimate land subsidence, and I'm showing you an example here for BKK 013, which is more in the north, where we have a more continuous description of subsidence from the model, and we combine that with the observations which are only available when we have a satellite with INSAR and INSAR data covering that period. But as you can see here, we obtained a reasonable good fit between those two. And the manner in which this has been calculated is described in a paper where Jenny was the main author, which appeared in Groundwater last year. And those of you interested in more details can, of course, download this paper. I will provide a reference at the end of my presentation. We start by an estimate of basin-wide pumping and combine that with the groundwater data, the aquifer heads that we have available at different wells, to then use the PASTA package to simulate the aquifer heads. That estimate of groundwater is then combined with a physics-based model to estimate subsidence. And the special aspect in that simulation is that we take into account the effect that the groundwater variations have on the compaction of the clay layers. So that's addressed in a separate module in our model. The simulated subsidence is then calibrated with the observed subsidence, as you saw in my previous plot, and that gives a reasonably good estimate. Now, in order to combine more observations and really improve the model so we can have better forecasts, Jenny worked on the use of data assimilation, where she not only estimated the groundwater state and the subsidence, but she also estimated the parameters of the different models in order to have better forecasts. And that's what is illustrated schematically here. When she applied the data assimilation, you see that also for wellness that were not performing as well as the one I showed before, like here the BKK 006, we really got an improvement when we assimilated the subsidence data. So we were very pleased with these results. There are still some aspects that need further attention because the region-wide pumping was not always in agreement with what the models rendered. But again, we follow this approach that I already showed you in the scheme, but that's laid out here in words. So a three-step procedure combining both the time series analysis of the PASTA's hydrological package with a physics-based model and the data assimilation, which is called the ensemble smoother multiple data assimilation method, to then obtain the subsidence parameters of the model, which allow us to do better forecast. What this picture also makes clear is that the largest variations in subsidence really occurred over the end of the previous century, going a little bit into this century, but at the moment subsidence levels are relatively low. As a last extension of our work, we had an MSc student, Tijmen de Boer, who looked at the combination of Jenny's subsidence results with different scenarios for sea level variation. And since he only had limited time, we focused on highly simplified scenarios where for these three regions, A, B, and C, Tijmen assumed slightly different sea level variations and or subsidence variations, and then assumed a sea level scenario of increased sea level height. And when he did that, he could demonstrate that especially this region A, the Samut Prakan region, is of risk when flooding would occur. And we do realize that this was a very initial study, just very exploratory, and that we need to take the topography and the subsidence into account in much more detail in order to get a more accurate description. We also realized that a lot of the impacts here are socioeconomic, and it would be really interesting to look more into an assessment of these impacts and really evaluate which regions are most at risk in that sense. So all in all, I feel there is a lot more work to be done, but I'm very happy that we have one article by Jenny Suntorn Rangsan, which you can find here. The thesis of Tijmen de Boer is available on the TU Delft repository. And Milan and Andrew have evaluated some more inside data, which hopefully Milan will present some of in a few hours. And I think that could really lead to more interesting work together with Wim Simons and Mark Naye. We're planning to submit another proposal so we can continue this beautiful project. We have tested the data assimilation framework on synthetic cases, but we were unable to publish that. But our initial results on the real cases are promising, so this is work we would like to continue. And with that, I would like to end my presentation, and I'm open to any questions that you may have.
So thank you so much, Femke. So are there any questions from the floor on or online? Yeah.
Thank you very much, Dr. Femke. That was a very good presentation. My question just from your last slide, number 21, your last slide. What is the name of the temple? Is it in Thailand?
I have to admit that I don't know the name of the temple. I remember.
Where
I remember visiting a temple with Wim last year, but I'm so bad in names that is Wim in the room? Perhaps he can answer this.
Maybe someone here can help you. Captain Soman, what is the name of that temple? I guess it's in Thailand. Khun Samut Jin or not?
This would be maybe different from the one that we visit last time. Khun Samut Jin, last time that we visit, should be maybe my Dr. Charirong suggested that maybe during the flooding time in almost in yeah. So thank you so much, Femke. So we move on to the next presentation. Will be Wim Simon. He will talking about how to use the GNSS to study the land motion in the usually for our installation is the vertical movement motion. But first, he would have the video presentation of his work. Can the team show the presentation of Wim? Thank you.